Now I will share my screen. Is it visible?
Yes, we can see your screen.
Okay. Here is the slides. Okay. Today we will discuss the following question. How to guarantee the existence of the stationary solution to equation with interaction. Yesterday we we write the equation with interaction, which describe the behavior of large system of interacting particles in the random media. We have seen that this equation is different from the ordinary stochastic differential equation. And the difference is that in the coefficients, we have not only position of the particles at the present moment of the time, but also we have the measure valid argument, which is mass distribution of all particles of the system. Nevertheless, it is natural to ask about the limiting behavior of the system, and one of the simplest and good examples of the limiting behavior is the existence of the stationary solution to some equation. Yesterday we mentioned that in stochastic case, we cannot expect the stationary point, but we can expect stationary solution to equation. And let me recall you the well-known definition of stationary process. The stationary process is such process that if we shift it in time in any value s, then the shifted process has the same distribution as initial. Sometimes it is called strictly stationary because there is another notion of stationary in square mean, but we did not work. We do not work with stationary in square mean, so I will call a strictly stationary process simply stationary. For discrete time, the definition is the same. Here is two examples of stationary processes. The one is most known, the sequence of ID random variables is evidently stationary sequence. And by the way, here we can see why the stationarity is important for solution to stochastic differential equation or for random dynamical system. Because on this example, we see that such results as the law of large numbers or central limits theorem are applicable to this sequence or to the functional from this sequence. So one can predict probability characteristics of different functionals or the behavior of the limiting behavior of some functionals from the process or from the system. Another one is obtained from the Wiener process, and it is a very nice and beautiful Lampetti transformation of the Wiener process. Just do such substitution of time, change of time in Wiener process, and in this way you get, by the way, a Stein-Uhlenbeck process from the Wiener process. Yeah? And it is easy to check now stationarity because we have a Gaussian process, and in Gaussian case it is enough to check the mean and the second moment covariance function. And if this covariance depends only on the difference of the arguments and mean is constant, the process is stationary. So we understand that it is desirable for random dynamical system or for solution to stochastic differential equation to find such case when it is stationary. Now let us look for tools how we can guarantee that the stationary solution exists. This is a main problem which we will discuss today, because when we will consider equation with interaction, we must have already some prepared tools to discuss the existence of the stationary solution. So let's begin. Begin with a very simple example, but very important. This is an example of linear regression. Suppose that sequence epsilon n are a IID sequence with a finite first moment. Consider the recurrent equation, and you see this usual equation of after regression, and it is easy to see that this equation has a stationary solution, like this one. One can easily check that this solution is stationary because of epsilon and IID, and we organize epsilon star with the same procedure, just shifting our random variables epsilon n. Then when we will shift index in xn star, then it is the same that shifting of epsilon n, but epsilon are already stationary. So it is a stationary solution. And it is interesting to see how one can invent this solution, because I give you just answer, but it is maybe good to know how to get such answer. And this solution can be obtained as a limit of solutions to Cauchy problem. Let us consider the following Cauchy problem. It is related to the same recurrent equation. Xn plus 1 is equal to 1/2 of xn plus epsilon n plus 1. But it starts from the 0, from the initial value 0, at the moment m. And we just produce the solution for moments of the time which is greater or equal than moment m. Then it is easy to see that our stationary solution is a limit when when initial time m small tends to minus infinity, tends to the past of our solutions to Cauchy problem.
I'm sorry, what is the equation in the Cauchy problem? I have not understood.
Here is it. Xn plus 1 equal to 1.
Okay. Okay.
The same equation. This is an idea. We have an equation and we want to have stationary solution. So I propose just to consider Cauchy problem for this equation, which start at the moment of the time m small, which goes to minus infinity. And it occurs that the solutions to Cauchy problem approximate stationary solution in this case. The same occurs to be true for nonlinear equation. For example, one can consider such equation which comes from stochastic approximation. You see yn plus 1 is equal phi from yn epsilon n plus 1. And suppose that this function phi, with respect to the first argument, I did not write the second argument, it is the same, satisfy Lipschitz condition with a Lipschitz constant which is less than 1, strictly less than 1. Then one can say exactly the same. The stationary solution exists and can be obtained as a limit of solutions to Cauchy problem with the same initial condition and starting time tending to minus infinity. So we can see that we already invent some way how to, at least to try, not to get, but at least to try to get the stationary solution to stochastic difference equation. We just take Cauchy problem with the time from the past and push this initial time to minus infinity. Then maybe we will get stationary solution. But what is important? Important is that we have here the constant alpha, which is less than 1. Here we have already 1/2, and maybe everybody understands that I can put instead of this 1/2 any alpha which have absolute value less than 1. This is the one idea. Second idea is related to the compact phase space. It occurs that if we have a system on the stochastic dynamical system on the compact phase space, we always have stationary solution. Let me show you examples. Suppose that psi n are independent and uniformly distributed on 0 to pi. Consider the following equation. Xn plus 1 is equal to, this equation is in the complex number, and this equation is especially on the complex circle with the radius 1 around 0. So now the phase space is compact, it is a circle, yeah? And we have such a simple equation. Xn plus 1 is just multiplication of xn on this exponent. Here I is the imaginary unit. And one can imagine this like xn plus 1 is a random n of rotation. And you can see that we just move this random n on the n psi n plus 1. Yeah? Now the solution x and m converge only in distribution when. So let's try to do the same. Let's start from initial time m small and push this time to infinity. But what happened? Our solutions will not converge as in previous case. They will converge only in distribution. By the way, this conversion is trivial because after multiplication, after the first multiplication on epsilon exponent xi n plus 1, we already get uniform distribution on the circle. So it is trivial that they converge only in distribution. But this allows us to use weak stationary solution. So this means that we construct a new probability space, we construct a new sequence xn together with the sequence xi(n), such that this equation holds and that xn is stationary. To do this, we just need one additional uniformly distributed on the circle random variable, and one can say that this random variable is x0. Yeah. By the way, one can prove that there are no strong stationary solution, and the arguments is exactly taken from the Cyril-Son example, well-known Cyril-Son example of the stochastic differential equation without a strong solution. This is just modification of this example. You see, we have compact space. We have not convergence in general, but we have weak convergence. Yeah, we can do the same. In general, one can even consider not the one special solution of Cauchy problem, but average of distribution of solutions to Cauchy problem when time tends to -infinity. This is, by the way, well-known principle, which goes maybe to Bogolyubov, Krylov, Khasminsky. So it is a very old idea, and you can see this idea in university courses when study Markov chains, and if we have if we have Markov chain on the finite set, then we always have invariant distribution. One of the proof is exactly the same. We consider the average of distributions to, say, to Cauchy problems. And we must have at least one limit point of these averages, and this limit points is already invariant distribution. So the existence, the stationary solution can be based on the following thing. We have compact phase space, or we just have some coefficients which glue up our solution which start from the different points. If we came back to these examples with regression, it is easy to see that if we start from two different points here or here, then our solution will tends one to other. So difference between solutions tends to zero. Actually, this is the reason why the solution to Cauchy problem have a limit when we push the time, initial time to -infinity. This is one idea. And another idea to find something which can be substitution of compact phase space. On the compact space, the average of the distribution of this Cauchy problem also must have at least one limit point, and this limit point can be the invariant distribution, so we can start with it and have a stationary distribution. Yeah? This idea also work with the continuous time, and let's see what happened for stochastic differential equation. The first example is Ornstein-Uhlenbeck process. It is well-known process. By the way, we get it already today using Lamperti transformation. And let's consider the equation for Ornstein-Uhlenbeck. This well-known equation, like d psi t is equal minus alpha psi t dt plus dw, where alpha is positive. Yeah? And you see this term, minus alpha psi t dt. If I suppose for a moment that there are no tw in the right-hand side, then the term near dt has a such form that our equation is stable. Yeah? So zero solution now is asymptotically stable. Every solution tends to it. And by the way, two different solutions which start from different points must have such behavior that difference between them goes to zero. So now we just add noise, and I suppose that W is defined on R. It is usual procedure. We just can take two independent standard inner processes, W1 and W2, and define WT as W1 when t is greater than 0, and W2 minus t when t is less than 0. Then the increments of our process W, which we built, are, roughly speaking, independent, identically distributed, Gaussian, and so on. So we can consider such stochastic differential equation on the all real line and look for stationary solution. And now let's proceed as we did before, because we have this minus alpha xi, which push all solutions together. So we just can consider the solution to Cauchy problem, which start at the time s from the zero. And then this solution, of course, has a following form. And it is easy to check that when s goes to minus infinity, it goes to the following integral, which converges because of alpha is positive. And it is easy to check that this is exactly stationary solution. So the idea that we move our initial time back to minus infinity again works, and we get a stationary solution to Einstein-Beck process. The same can be done in more general case. Here you see nonlinear stochastic differential. Again, if alpha is positive and sufficiently large, it must be larger than derivatives of A and B, or Lipschitz constant of A and B. Then one can again do the same and check that the solution to Cauchy problem with the initial time going to minus infinity have a limit, and this limit is a stationary solution for such nonlinear stochastic differential equation. But let me note again that this equation is constructed in such a way that all solutions tends one to another when t tends to plus infinity. Yeah? Okay. Now let's look for idea of compactness. Of course, one can consider the special kind of stochastic differential equations which already live in compact space. It can be done, yeah. But it is not very interesting. So we must have the coefficients of such kind that all trajectories of solution to this equation spend a lot of time in some compact. This is the idea. How to organize, how to check that the coefficients of our equation have the following property. And this can be achieved via Lyapunov function method. Let me recall you that it looks like, consider the stochastic differential equation. dxit is equal h from xit plus bxit dw. Definition. The function v, which x, I consider one-dimensional case just for simplification, but of course it can be multidimensional for sure. The function v which are acting from R to 0 plus empty, is called by Lyapunov function for this equation if V is smooth, 2 times continuously differentiable. V from U tends to plus infinity when absolute value of U tends to plus infinity. And the generator, our process, this is a 1/2 B square second derivative of V plus A, the first derivative of V is less than 0 for U which belong to R. Then, if such a function exists, in most cases, we have the stationary solution, at least in weak sense as before. Of course, this method was considered by the huge amount of authors in different monographs. You can find it for stochastic differential equation, different modification, and so on. For example, it can be the condition that this is non-negative, can be hold only outside of some bounded region and so on. There are a lot of generalization and discussions of Lyapunov methods, but nevertheless, if we have such function, we get the stationary solution. The idea why it works is the same as I said before. We can use Bogoliubov averages of the Cauchy problem solution related to initial time, which tends to minus infinity. And this existence of the Lyapunov function will give us the existence of at least one limiting point in weak sense for this solution, for these averages. So we can see two main sources of the existence of stationary solution for stochastic difference or differential equation. One is the structure of coefficients which push all solutions together, and another one is the existence of the Lyapunov functions, which give us that our solution live in compact most of the time. So now let's go to equation with interaction and see what problem we will have when we will try to apply this method to equation with interaction. So let's start with new problems which we have. Let me recall you that equation with interaction. Consists of not only equation for separated particle, but for measure which describes the mass distribution of all particles. So, if we will have stationary solution, then we must have invariant distribution in the space of probability measures. So we can start with such thinking. Okay, we have, as we mentioned yesterday, Markov process in the space of probability measures. Maybe if we have such coefficients of equation with interaction that we can bound our measures in some sense, then we will have a stationary distribution, stationary solution. Yeah? But it occurs, unfortunately, and this is the first bad thing, that it turns out that the space M with M small, indices M small, this is a Wasserstein space of probability distributions on RD which have m's finite moment, is not locally compact. Is not locally compact. So let us see a proof. The proof is simple but important. So consider closed ball B mu R in M. And we will see that this closed ball for positive R is not compact. Take a sequence UN in RD such that this norm of this sequence tends to plus infinity. And choose epsilon greater than 0. And U0 which belongs to RD such that this alpha equal to mu b U0 epsilon is greater than 0. By the way, let me make a remark that epsilon can be arbitrary. We always will find such U0 because we know that the support of probability distribution on RD is non-negative. Now define mu n as follows. We just have a restriction of the measure mu on the outside of the ball b u epsilon 0. Then put alpha n delta u0, so concentrate the mass in the center of the our ball, and plus alpha minus alpha n delta un. Here I take alpha from the interval 0 alpha, and we will choose it in the future. Then it occurs, and we discuss it with you how to estimate the Wasserstein distance. Here it is very easy because it is a distance between measure mu and mu n. We have common summand, and we just need to estimate the distance between the measure mu, which is restricted on the ball with these two delta measures. And it occurs that the Wasserstein distance between mu and un can be estimated as alpha n multiplied as such integral over the ball, and plus alpha minus alpha n such integral over the ball, where we have here un, not u0 but un. Because we have these two delta measures, one concentrated at the point u0 and another one concentrated at the point un, so it is natural to have such estimation. Now choose alpha n and epsilon in such way that epsilon is less than r over 2. Let us recall that I mentioned we can choose epsilon in any choose epsilon arbitrarily small, and we just take this alpha minus alpha n such that this limit is equal to r over 2 in m. It is also can be achieved because the integral increases to plus infinity. So we take alpha n in such a way that get this limit. Then from one side, mu n belongs to closed ball mu r. This is because of this estimation. And from other side, this sub over n u minus u0, here we have integral u minus u0 greater than c of this difference u minus u0 minus un over mu n is greater or equal than upper limit where n tends to infinity, more mu minus un, m alpha minus alpha n, and this is greater than 0. So you can see that the condition of weak compactness, which we already discussed in m small, doesn't hold. So we see that closed ball in the space Mn is not compact. Then one can ask, but if we cannot apply the idea of Bogoliubov and we cannot apply this Lyapunov functions directly, what we can expect? Let us look for some examples of what can be natural behavior of solution to equation with interaction in stable case. We mentioned with you yesterday that equation with interaction is the description, mathematical description of the system of interacting particles, even without a random noise in the right part. And one of the most known such system was the Kuramoto system for connected oscillators. Let me recall you that we already were succeed to rewrite this Kuramoto system exactly in equation with interaction because we have seen in the right part the integral with respect to empirical measure of the particle. So now we can consider the system for arbitrary measure mu zero, which is not necessary discrete. And this is how to say, a very interesting example for us. Why? You see in the right-hand side the interaction between particles, double interaction, which is described by the function sine. And the Lipschitz constant of the function sine is 1. Yeah, we cannot say that it is less than 1. Also we have no additional terms which push our solution which start from the point u to some fixed point, say to 0. So we cannot expect several things. We cannot expect that our solutions will go to the fixed point, yeah, like 0. We cannot expect that our solutions will go one to another because of the Lipschitz constant is only 1. But people are interested in the Kuramoto model, in the synchronization theory, and they know that the behavior is the following, that there exists the phenomena of partial synchronization. What does it mean? It means that when we start from the distribution, from arbitrary distribution of the circle of our angles, because let me recall you that x now play a role of the angle, we can consider our equation not on the r but on the 0 to pi, yes. Then what will happen? Our our solution corresponding to different particles will not go one to another, but they are in some sense concentrated and floating together around the circle. So they begin to move more or less together. The particles does not collide in one particle, but they move together around the circle. And in the theory of synchronization, people always pay attention to this example because connected oscillator became to be moved in unison. Yeah? So one can try to watch the same behavior for general equation with interaction with noise. And it occurs that it can be done. Let's consider the linear equation with interaction, but with the noise. Yesterday we considered such kind of equation without noise, so it is familiar to us, and it looks like that dxut is equal a matrix A multiply on the difference xut minus integral over rd v mu t dv dt plus dw. So I suppose that we have now just one Wiener process, and we have such equation. Then for center of the mass, we denoted it by m indexed by t, which is equal to integral over dv mu t dv. We of course have the following equation. D mu t is dwt because the term with dt will disappear after initial additional integration with respect to mu t, with respect to mu zero. Then center of the mass has the following description. It is equal to initial position m0 plus wt. We already have the center of the mass in our case is floating over the space as a Wiener process. Now, for difference dxut minus mt equal axut minus mt, we have the deterministic equation. So xut will be equal mt plus the exponent of at. This is semi-group related to matrix at, u minus m0, and equal wt plus exponent at, u minus m0. You see the following precise form of the solution, and now we can analyze it. In the case of ordinary differential equation, we have the following conclusion. If A is such that the semi-group is contractive, then also solution goes to zero. And in opposite case, we have a solution which goes to infinity. Yeah? But now, let us suppose that the semi-group is such that operator norm is less than 1. Then what happened? Then mu t is concentrated near its center of the mass. Mu t will not spread over all space. But that's all what we can say. This mu t is floating over the space. The picture looks like follows. We have some clouds. This is black cloud that is in my imagination the measure mu t, and of course this cloud has not grown in size, but this cloud is floating over all space with the process W. And evidently, it is not expectable that our equation has a stationary solution. So, what one can say that we have two troubles related to the question of existence of stationary solution for equation with interaction. The first is that the space of probability measures equipped with Wasserstand distance is not locally compact. And another one is that we have a very special coefficients. You remember on the last lecture we discussed that natural coefficients to equation with interaction are related to multiple interaction between particles. So multiple integrals with respect to measure mu t from some kernel. And this example shows us that even in a case that kernel has Lipschitz constant for difference less than 1, we can say that this A is a contractive operator. Even in this case, we have not a stationary solution. But what we can do? We can try to formalize this this notion of partial synchronization, which came from the discussion of the Kuromoto system. So in the next lectures, we will, in the next lecture tomorrow, we will do several things. Firstly, we will try to go by the traditional way for ordinary stochastic differential equation and still try to get the stationary solution using special coefficients and which push our all trajectories to some point, namely to 0, for example. Then we will see interesting but very pure behavior. All mass for stationary solution must be concentrated in one point. So in this case, we will prove that stationary solution is concentrated in one point, which is moving over the space. Secondly, we will see what happened if we suppose that every particle has its own center of attraction. We will see some interesting phenomena. And finally, we will try to formalize this notion of partial synchronization, which will give us possibility to invent some not stationary, but close to stationary behavior of the equation, of the solution to equation with interaction. So it is natural to stop now in order to have positive statement tomorrow. Thank you for attention, and maybe somebody have questions or comments, please.
Yes, I have a question.
Okay, please.
Okay. Can you show the last example where we stop here? Yeah. I don't understand why we obtain the equation for the center of mass a little bit below, next line below.
It is a good question, and it is one of mathematical tricks related to linear equations with interaction. You see, this integral over Rd V mu t dv can be rewritten by a changing of variables formula. Then it will look like integral over Rd x from V mu 0 dv. Mu 0, yes?
Yeah.
And mu 0 is the deterministic initial measure. So what we are doing, we just integrate this equation again with respect to mu 0. What we will have? We will have in the left part differential of the integral of x ut mu 0 du. This is exactly differential of the center of the mass. Yes?
I have to calculate, yes, but I understand the idea. Yeah, thank you.
Yeah, and then when we integrate everything, we get that we cancel these two integrals under sign of A and get the equation for the
Mhm.
center of
Thank,
the mass.
thank you.
You're welcome. Okay. If there are no other questions, then thank you for your attention and see you tomorrow with the investigation of almost stationary solution to equation with interaction.